getting a tenure professorship at Harvard faculty, where she was also chair of the physics department later on. She was involved in the discovery of the last and the heaviest top quark, which was an extremely exciting final discovery in the quark world of nowadays. And today she's working also moving up in energy at the Atlas experiment at LHC. Many prizes, awards and honors. And the talk of today will be Maria and me interested in long-lived particles. Thank you very much, Melissa, for joining us.
Hi. Well, I can't see any of you, but I'm happy to talk to you. And my talk is going to be a little bit different. I wanted to talk about my first role model that I had just recently. I'm 66 years old and I just got one recently. And it turns out that we're both interested in similar things. So I just want to tell you the story of this. We're interested in the lifetimes of particles. About, I don't know, 5 years ago, I can't remember when this was, I was asked to give a lecture, the inaugural lecture for the Maria Geppert-Mayer lecture at the University of Chicago. And I had heard of Maria Geppert-Mayer before, but I didn't know much about her. And when I asked the organizers what I should talk about, they said, talk about whatever you want. And it turned out I decided to talk about Maria Geppert-Mayer because I found her really, really interesting. And now I want to sort of tell you why I found her interesting, and also the kind of physics she worked on compared to the kind of physics I work on. So the first thing I did when I go to Google and I look up Maria Geppert-Mayer, and I see that she, after leaving Germany, and I'll talk about that, she came to Sarah Lawrence College in the United States. And this was a faculty meeting, and Sarah Lawrence College was then just for women. So they had a lot of women faculty. And I looked at this picture and I thought, that's interesting. Maria Geppert-Mayer is the one on the left. And I just looked at their feet. I looked at the feet of all the professors, and I noticed that all of them had their legs crossed except Maria Geppert-Mayer. And so I sort of looked more closely at her feet. You see them there on the trestle. And I thought, I think she's kind of interesting, the way she's holding her feet. She might be an interesting person. Then I saw a picture of her like this. And she looked to me exactly like I thought I would want to be looking, like very intense and serious and kind of, you know, like an intellectual, like a philosopher maybe. Now I realize she's smoking a cigarette and it's not a good thing for all you young people to do, but in those days, it was sort of a statement about the intensity of how much you wanted to spend your time thinking. And it reminded me of three people who I thought were really interesting similarly. Of course, they're all smoking cigarettes. Again, please don't smoke cigarettes. But Susan Sontag was a famous intellectual in the US. Marguerite Yourcenar was a famous French author, and Chantal Akerman was a famous Belgian filmmaker. And I thought, okay, these people look sort of similar. I really want to learn more about Maria Geppert-Mayer. And then you may say that I'm, you know, a little bit superficial, but she turns out to be really, really interesting. I was right. So she was at Goethe-Universität. I probably said that wrong for all the German students there. And she was there in the early 1920s when pretty much every single person who's interesting was there. I named many of the people right here. Here she has a picture of herself and her Nobel Prize winning PhD advisor, Max Born. And she was taught by the very famous and amazing mathematician, Emmy Noether. Again, sorry about my pronunciation. And of course, the one on the top with the nice hat is David Hilbert, who lived down the street, down the hill from her, and she had to pass his house every day on her way to university. So, and this is really just to say, Emmy Noether, recently I saw a one-woman show about her life, and one thing I realized was that we don't, for these women, both Maria Geppert-Mayer and Emmy Noether, we don't have a lot of writing that they did so that we can, figure out what they thought about various things. They did a lot of writing about mathematics and physics, but not so much about anything else that was happening in the world. And this brought me to think that I would like all of you young women scientists to start writing every day, so that if you do something amazing and then you die, we'll know what you thought about things. For instance, Hermann Weyl, who was also a mathematician, wrote about Emmy Noether, and he described her as being, is like, when you're with her, it's like being with a warm loaf of bread, which is both nice and strange. But he was writing and she wasn't. So hopefully all of you will start writing every day and then discover something amazing. So Maria Geppert-Mayer had an interesting life. She was actually born in Poland, like Marie Curie. She moved to Göttingen at 4. She started to study mathematics, not physics, and then switched to quantum physics. She got her PhD in 1930. And then she moved away to America in 1930 because she fell in love with an American chemist. And she came here, and since they were both really good scientists, her husband always got a job, which meant that she couldn't get a job because of something called nepotism, because they were married. But she did a lot of physics, and she worked in a lot of places and met a lot of interesting people. She was at on the Manhattan Project, which is an interesting thing since she was a German citizen. The Manhattan Project was the American atomic bomb project. After the war, she went to the University of Chicago, where she wasn't paid, but she was given a position at a nearby laboratory. And then she did her really interesting work, which I'll talk about. And finally, she went to the University of California, San Diego, as a professor in 1960. She received the Nobel Prize in 1963, and then she died in 1968. So she was always asking about lifetimes. In particular, one thing that concerned her was why certain elements are stable and certain isotopes are stable and others are not. And here I just show you this Physical Review article because she wrote it by herself. And I've never written a paper by myself, but I'd like to. So that in that sense, she's my role model. She was a theorist, and I'm an experimentalist, so that's also a problem. Here's sort of what she was thinking about. If you look at all of the isotopes and you look at, on the x-axis, the number of neutrons, and the y-axis, the number of protons, you find that there's some isotopes which are stable, these black guys, and there's some which are less stable. And the question is, do we have a nuclear theory which can predict that? And that's what she got the Nobel Prize for coming up with that theory. But I like her also because she was a theorist who looked at data. So, of course, if you want to know about all the isotopes and whether they're stable or not, you actually have to make the isotopes and then measure how long they take to decay. And so she realized the importance of hanging around with experimentalists, in this case, at a cyclotron, which was only 7 MeV particles at the University of Chicago. and they were able to create krypton and xenon isotopes that she later used in her paper in order to make her theory. So this is just the atom that she works on that I also work on. I'm actually, more interested in elementary particles, but maybe only because they'd already figured out everything about the nucleus. And I say that, which of course is not true. The last talk we heard points that we're still learning a lot about how nuclei interact. So the one other thing that I thought was really good is her thinking about physics. She says there are two ways in which physics tries to obtain a consistent picture of the structure of the atomic nucleus. One of these is the study of elementary particles, their properties and mutual interactions. That's me. Thus, one hopes to obtain a fundamental knowledge of the nuclear forces from which one can then deductively understand the complicated nuclear structures. The other way consists in gaining by direct experimentation, which is what they did there, as many different data as possible for each individual nuclei and examining the relations among these data. One expects to obtain a network of correlations and connections which indicate some elementary laws of nuclear structure. These two ways have not yet met to establish a complete understanding of the nucleus. She wrote this before, although many connections have been found. And this is one of the few things, I mean, she wrote a book about nuclear structure, but in the book, there are once in a while little pieces where she says what she thinks about the way physics should be done, which I find really interesting. So as a particle physicist, she did a number of things which were kind of interesting. We learned about beta decay, neutrons decaying to protons, electrons, and neutrinos in the 30s, and she immediately wanted to know, well, what happens if two neutrons beta decay at the same time? And she wrote a single author paper about that. The other thing she did, just so you know, in this double beta decay disintegration, we're still very interested in seeing some aspects of this, especially when there is, in these beta decays, no neutrinos actually come out. And there's currently 10 experiments studying this still. And this was a paper she wrote in 1935. The other thing I thought was kind of nice to point out was a paper she wrote with Edward Teller. Edward Teller was a Hungarian emigre who she met, who was also the father of the hydrogen bomb. So not a person. So I don't know if you've ever seen the movie Dr. Strangelove, but he was the model for Dr. Strangelove, the crazy scientist. But they were best friends, and a lot of the people who came from Europe in the 30s kept very close with each other. For instance, Maria Geppert-Mayer was also very good friends with Enrico Fermi, and they worked together at the University of Chicago. But this was an interesting paper because they just looked at the Earth's crust, and they said, let's see the abundance of the elements and see if we can understand why this would be. And you see here on the y-axis is a log of the abundance of that element. So it starts with hydrogen, and on the x-axis is the z is the charge. And what they noticed was that after iron, which is at something like 25 or 26, there's a sharp fall off. And so they asked the question, where did these higher elements actually come from? Where were they made? Were they made in stars like everything else, or were they made in somewhere else? And so what they decided was that in this paper, they decided that actually things like gold actually came not from just star collapse, but they had to come from something like neutron star merging. So if you look at this periodic table and you look at, this is a periodic table which it tells you where these different elements came from, and you can see these purple things were from merging neutron stars, which is kind of an interesting idea. And it's a fact. And so the interesting thing is, like in 2017, a gravitational wave experiment, LIGO, saw a big signal from neutron star merging. And then the people who look at the sky and try and figure out what elements are there, so they do spectroscopy, actually found gold and the higher elements, platinum and gold lines. And so this is a kind of nice thing. It's kind of weird to think that a long time ago, before the Earth was made, neutron stars merged and gold came out, and then the gold, we sort of went into the dust of the universe. And then when the Earth was made, some of that dust was gravitationally attracted to what became the Earth. And then we got the Earth, and then the gold somehow came together in the Earth, and then people went digging for it with picks, and now you wear gold jewelry. It's kind of an amazing path from neutron star merger. So she worked on that. I can't tell whether you guys find this interesting because I can't see you, but I'm just going to guess that it's totally interesting because I find it interesting. So this Edward Teller is a very famous guy in America, and they had a very close friendship. And I went to her archive in San Diego, and I found something like 200 letters from Edward Teller to her. I found no letters from her to Edward Teller in his archive at Stanford. But I love the first lines of these just to show you the kind of friendship they had. When we talked on the phone today, I felt like a heel. So in American, that sort of means like a jerk. This hotel has 27 floors, and I have a room on the 27th. I just think this is I am most conscientiously practicing the art of being lazy. I just think I read all of these letters, and I found them very interesting as a document of how collaborators talk to each other, but also how emigres talk to each other in a strange land. Someone from Hungary, someone from Germany, they come to America during a strange time, and they join together because they really miss where they come from. So that's Maria Geppert-Mayer. Very briefly, I have much more to say, but I'm supposed to say something about physics. So in a role model situation, there's the role model, and then there's the person. And unfortunately, I'm this person in the middle, the cowboy, cowgirl. But I'm actually just what do you call it? I'm the sheriff and my cowboy boots. But that's who I was, but I really wanted to be these two people. They're more modern cow wranglers. I like them. But the other thing is, I'm sort of I sort of feel like a cowgirl who wants to get on the horse and go to the frontier of science and find something. But I also feel like this 16th century Chinese poet who sits on his horse, drinking wine and thinking about watching the moon and thinking about home. So I think there's some idea that I liked Maria Geppert-Mayer because she seemed to have kind of wistfulness and a kind of cowgirlness about her, actually much more than me. So anyhow, that's why she's my role model. But also, I'm an experimentalist. And so instead of writing papers on theory and having single author papers, I work with 3,000 people. Oh no. A forklift just went by. 3,000 people. So I also find, though, in experimental physics that there's also amusing and lovely people. So Marie Geppert-Mayer used accelerators to make the isotopes that she used to figure out about the nucleus. I do similar things, but not about the nucleus. But there is one guy I think it's worth for any young person to notice it. So there's all the things they tell you in school that you should be good at, and you should do right, and you should do all those things, and also don't smoke. However, you should also have a sense of humor. So here's the first collider. I work on a colliding particle experiment, colliding protons together, which I'll talk about if I have time. I'm just checking the time here. Oh no. So this is a situation where you take a photon, it turns into an electron and positron if you put it through material, and then you collide the electron and positron. And the man who made this first accelerator wrote this. He said, the following is a very sketchy proposal for the construction of a storage ring in Frascati. No literature has been consulted in its preparation, which I think is very, very funny. Since this invariably slows down progress in the first stage, necessary though it may be in the consecutive stages of development. So this is a very interesting thing. I'm sure everyone has told you, whatever you do on a new project, that you have to do a literature search first. And he says, this is the proposal. He says, no, I have not properly read O'Neill, which was a reference, but I hope that somebody will. So this is the beginning of CERN. We had really big dreams. So CERN is where my collider is. And these are two guys, and this is the groundbreaking at CERN. And you see these two guys here. I've shown this picture many, many times. And at some point I realized in the groundbreaking that there were two very similar guys. Do you see them? It doesn't, I know, and nobody's laughing because it's so funny. Anyway, so sorry. This is the groundbreaking. We had big dreams. Now we have something which is 27 kilometers long, and this is where I work. And I'm also interested in lifetimes. Unfortunately, a lot of the lifetimes of the particles I've worked on are very short. So the lifetime of the top and the Higgs are less than 10 to the minus 23 seconds. So that's not really something interesting. So I decided, after building the detector with short people, I decided to think, can we find some new particles that have longer lifetimes? And then can we be happy? So what I'm going to do is I'm going to search for new physics by looking for particles that have longer lifetimes than anything I know, or have longer lifetimes than most particles, but I don't want them to be stable. So the neutron on the right here, the neutron, the proton, the electron, the proton and electron are stable as far as we know. The neutron is about 15 minutes lifetime, and the muon 2 microseconds. So can we find some interesting, very high mass particles which have long lifetimes, and by their lifetime, we can characterize them and say, this must be new. I don't know any particle that has this lifetime. So that's the whole idea. And very quickly, I'm going to say, how do you find a particle with a not so long lifetime? Well, you need to use just the first part of your detector, because the particle might go all the way through your detector, or it might stop at some point and decay into other particles. So what we want to use is just the very inner part of our detector. And that is this central part where there's a silicon detector, a detector made of silicon, which is a tracker. It tracks charged particles. So what I'm looking for is a signature. So the particle comes out here. You see that right in the middle here, there's a blue charged particles coming out. And then there's a particle that I think, oh, this could be interesting. It looks yellow, and it's going to go through my silicon detector, and it's going to leave some energy. And if it's a very massive particle, it will leave more energy than normal. And if it's a very massive particle, it will also have a velocity, or a beta, which is velocity over, so there's my timer. A velocity, beta is the velocity over the speed of light. So most particles will go almost the speed of light, but if it's a very massive particle and it's going, through my detector, then it'll go more slowly. So what we're going to do is we're just going to look in this pink part of the detector, and we're just going to look for any signal, any track that has a lot of energy loss. And you may say to yourself, well, why would it have more energy loss? And I will tell you, there was a guy called Beta and a guy called Bloch, and they figured it out, and they showed that if the x-axis is beta gamma, and the y-axis is energy loss, then if you have particles going slowly with a very high mass, so P over M is low, then you will have you will have a lot of energy loss. So you got to just believe me, because I can't actually teach you that right now. We're going to have more energy loss. So here's the equation, which you might know from undergrad. So to find heavy particles, we have to know that beta gamma, where gamma is the relativistic gamma, equals the momentum of the particle over its mass times the speed of light. So this is so great. So if I measure the energy loss, and I say the energy loss from my last plot is correlated with beta gamma. Great. So if I measure the energy loss in my silicon, I have beta gamma. If I measure the momentum of the particle in my magnetic field, then I can find the mass of the particle. And this is a way I can find new particles. That's kind of cool, right? You know what I really like about this is I really like that it's sort of theory independent. However, there's some really great heavy ion, like the last talk, heavy ion detectors that can show you really why this energy loss on the y-axis is so beautiful. It can tell different mass particles, it can separate different mass particles. So here you see that the kaon, which has a different mass than the antiproton, has a very different signature, or the deuteron, or helium-4, for instance. So you can use this, we know that you can use this energy loss in order to tell the mass of a particle. So can we find something new? And what would the new thing be? Let me just see what time it is. I can't remember when we started, but someone's going to give me somewhere a time.
Yes, this is my job. Continue, don't worry.
Don't worry, don't worry, be happy.
Don't worry.
Don't worry, be happy. Okay, so here's the thing. Here's a very nice picture of all of the elementary particles in the world, plus some that don't exist yet. So the inner circle has all of the quarks and leptons and force carriers, the Higgs in the middle. And then these weird ones on the outside are what, if a theory called supersymmetry really existed, then they would exist. So in the real world, there's a gluino. In the supersymmetric world, there would be, in the real world, there's a gluon. In the supersymmetric world, there would be a gluino, for instance. So far, everybody loves supersymmetry as a theory, but there has been absolutely no evidence that it is a correct theory. No one has found any of these outside particles. But what we do at the collider is we collide protons together, and our guess is that if there were these gluinos, two protons coming together could make two gluinos, and then they could decay into real particles and some missing energy. So maybe if these gluinos went through our detector, we could see them, and they'd give more energy in the silicon. And so here is just, if we look at different mass particles and as a function of beta gamma, then we can see that they're different. So you could actually tell the mass of the particle by looking at beta gamma, which we know is d dx. So we did this analysis, and weirdly, we found this is the mass of the particle that we're looking for on the x-axis, and the number of events we see, and the blue line is what's expected if there's no new particles. And the black dots are what we find. And usually when we have something like this, we go, holy cow. But for this conference, I would just say, wow, this is really different, right? You would say, if you were in school, you would say, that doesn't fit. The blue line does not fit the data. Go back to the drawing board. But in the way we think about it is, this is a more than 3 sigma statistical variation from the blue line. So we're very excited about this. However, just to dampen all your excitement, in case you were excited, we looked a little bit further. We thought, well, if this is a high mass particle and it's going to leave more energy, it's also going to go slower. It's not going to go at the speed of light. It's going to go slower. So we looked to see whether this excess was going slower, and unfortunately it wasn't. So we don't know what this is, and that makes it even more exciting. So I wanted to finish just by saying that when I was in Oxford one day, Oxford, England, I went to this incredible museum, and it really smelled the formaldehyde, but other than that, it was really great. And it had this it's an incredibly beautiful building. I forget who the architect was, but all the way around this courtyard that I'm showing here, there were statues of great scientists. And I thought, well, that's cool. And then I realized that there were none of them were women. And then I kind of started crying, because I thought, wow, so many, years, so many hundreds of years where people were doing interesting things in science, women weren't really involved. And how what a loss that was. I mean, nothing to do about today, but just that was a loss. So I thought of going back, and if anybody wants to help me do this, of reconstruct a head of Maria Geppert-Mayer and then go in one night and cut off one of their heads and put this on. Also, don't do that. But I just thought that it's a much more exciting time now, where we have things like this WOW conference, and we can imagine doing all the science we want to do all the time without smoking. Thanks.
Thank you very much, Melissa. That was a very nice, exciting and intriguing talk. Thank you very much for sharing your role model and becoming yourself for us a new role model. Thanks for all the good advices. Don't smoke, don't destroy statues and monuments. So now our chair, Laura, has promoted more and more people to panelists, so you can ask questions yourself. Please raise your hand so that we have a smooth transition to our round table that will happen next. I have now 3 panels to check for questions. So meanwhile, let me start with one still on the science. So assuming we have no supersymmetric particles to find, where is all the mass so that we should see in the universe? Where is all the dark matter? Where is all the dark energy? And especially, how do we find it? How do we look for that?
Yeah, that's a really good question. So, well, you know, it could be tiny black holes. You know, we don't know we don't know the answer to the question, but there's still some candidates left for what dark matter could be, including tiny black holes, including, you know, gravity, not understanding gravity correctly, although that's somewhat ruled out. There's still some hope that there are WIMPs. And, you know, not everybody has given up on supersymmetry, by the way, just so you know. But I don't know the answer to where all the dark matter is. And unfortunately, nobody does. But
maybe also here we need a more energetic accelerator.
So that's interesting. I was talking, I read a book, a new book, that's actually pretty good, from Princeton University Press, about dark matter a couple of weeks ago. And I had I talked to, you know, maybe this is something people want to see. I talked to the author in a book talk, and it's online. And I asked him that question, you know, what do you think? And interestingly enough, he thought that colliders were not the place to look for dark matter, because when you look for dark matter in collider, you don't know for sure that it's dark matter. You know that it could be consistent with something, but so dark matter is something that if you produce it in the collider, it's just missing energy. You don't see it. It doesn't interact, so you don't see it. So there's lots of things that can make missing energy. So maybe collider is not the best place to do dark matter. I'm not sure I agree with that. I think we should do it everywhere. So it's getting hard though, because the underground experiments, you know, where they put something underground and hope that the dark matter, the river of dark matter flows through it in the galaxy, you know, those are almost coming to the point where they're not going to be sensitive to anything but neutrinos anymore. So I don't know. I wish you guys could come up with an answer.
Meanwhile, I have another question from Barbara Jacek.
Okay.
Thank you, Melissa, for this extremely interesting talk and historical perspective. I have a question I'd like to ask you, given that this is a wonderful first Women of the World in Physics conference. But to ask my question, I would like permission to share my screen, if that would be okay with you, Melissa. Okay. So let's see, you don't have a big black marker across the screen, right? And you can see it?
Yep.
So this, what I have here, and Melissa, please don't get depressed. This is the San Diego Union Tribune, and it was published in 1963. There's a nice picture of Maria Geppert-Mayer. And look at the title. San Diego Mother Wins Nobel Physics Prize. I don't think that would happen now. Am I completely sure? Maybe not, but I was wondering, Melissa, if you might comment on, you know, where are we compared to where we were in 1963?
Well, you know, one of the reasons I give this talk about Maria Geppert-Mayer is because nobody knows who she is. Like, everybody knows who Marie Curie is. Nobody knows who Maria Geppert-Mayer is. And why is that?
All my students know.
All your students know?
Nuclear physicists know. But yeah,
right. But if
probably she's not famous the way she should be.
Yeah. I mean, the public. I gave a talk to 400 people with PhDs the other day. It's not in physics, but you know, almost nobody knew who Maria Geppert-Mayer was. So there is a sense in which you know, she was not treated well. And that's what I like about her even more. Like, she just did physics no matter what. She was really interested in physics. But in those days, you know, people had a hard time thinking straight about women scientists. I don't know. I think obviously it's so much better now. Now when, you know, when a woman wins the Nobel Prize in physics, it's really kind of very exciting, and nobody talks about their husband or their children really.
Although I did see an article about the dress that a most recent woman Nobel Prize winner wore to the Nobel ceremony.
Well, the great thing about Maria Geppert-Mayer is that she drank a lot, which I also like. And when she went to the Nobel Prize ceremony, she also had a stroke, and her dress fell off her arm, so she looked very sexy in it. I don't know. You gotta like her because she seemed so vulnerable and just did physics all the time. You gotta really love that. Yes, I don't know. The world is a lot better than it was. And if we're like Maria Geppert-Mayer, we just do the science. Yeah.
I mean, if I